scolding you all for not being hip enough. So anyway, so there's the policy iteration part. You know, in the end, I don't expect you to absorb all that. I'm not going to be able to test you on it, but it is beautiful, and I hope someday you'll come back and read about it. You know, the other part, the LP, you really should understand that. You know, it's an algorithm that's interesting. I don't know if I can give you a homework assignment, but you should know what it is. So what it was is, again, is it's sort of like the obvious thing you might do if you're thinking about an ergodic, average cost problem. You know, I minimize. I was using this. This is a notation that's used in the notes, just because it looks like linear programming notation, but it just means I've used that notation, and I've used the dot product notation. Obviously, I do that to save chalk. And I do that in the notes just to scream it's a linear programming, you know. But subject to, I'm not going to say what it is again, gamma is in some script set G. And you know, G is a polyhedron, okay? And it turns out that this is this beautiful fact, the corners of this point. So a polyhedron is the convex hull of a bunch of points, the extreme points. And these extreme points correspond to deterministic policies, you know? Well, looks like that. So every corner, so there was a probability law here, randomized policy. Well, it's not randomized anymore. You know, it's 1 if u equals c of x and 0 else. And I feel bad. Sometimes I forget about history. I should tell you, this is Mann in 1960. Probably really due to Bellman, but anyway. So around the time when all this great stuff was happening, you know, in the 50s, Bellman was creating all of this. Now, if I tried to slip in that you can put an auxiliary, you can add additional constraints. So I could say gamma's in G, and, for example, just one extra function. You know, all right, and but that's a half-space constraint. You know, so this gamma, you know, even though it's a matrix, just stretch it out into a vector. It's a vector in Euclidean space, and saying a dot product is less than a constant defines a half space in Euclidean space. So what you're doing when you introduce another constraint like that is you're putting a dotted line there. That's a set of all gamma such that gamma dot C1 is equal to eta bar 1. All right. And then you have a half space beneath that, maybe, or either on one side or the other. Let's just pretend it's this direction. Right? So this half space is that additional constraint. So what you see, what you've done is you've cut off a corner. So there was a deterministic policy there. You know, these extreme points are all defined by deterministic policies. You know, I should really maybe put an I there, and an I there, and an I there, I. You know, there's a finite number of policies. You've got a finite action space and a finite state space. You know, so I've thrown away that ith corner, right? And I've created two more. And that's where the randomization comes in. So that point there is a convex combination of those two. And that's where the randomization comes in. And so he came with a perfect characterization of what can happen and all that. It's really, really cool. And here you can see why with one constraint you randomize over just two policies, basically. You take it, that's what ends up happening. With 5 constraints, you randomize over 5 at most. Yeah. All right.
Can you kind of I guess, help me see why the vertices are the policies of,
why are they deterministic?
They're the gammas of that form.
Yeah.
Why are those the vertices? This is cool if that's true. But
Yeah. So, it's actually constructive. You can take any gamma and you can compute the corners. You can actually do it constructively. You can write for any gamma in G. There you can find some beta I such that gamma is equal to the summation of beta I, gamma I. And it's constructive. You can actually work out the coefficients beta I. Yeah. So this is a convex combination. So the summation of beta I is 1. And each of them is greater or equal to 0. Yeah, so it's constructive. And that's why it's hard to write it down. It's because you can actually get a formula, but it takes some chalk. Yeah. What's that? Oh, yeah, that's right. There's actually, but that says that that's the other direction. That's if you know the extreme points of this form. Yeah. No, so this is a definition of extreme points. But the fact that you can go the other direction, you see. I can, for any gamma, I can find these beta i's such that these are deterministic, are of this form. So I'm trying to prove that the corners are this. Yeah. Okay. And you do it by construction of the betas. You just show that beta 1, you have a formula for it. You get a bunch of linear equations and solve them. It really is just that. You make this presumption, and you get a matrix equation, and you say it's solvable. There might be a more elegant way of saying that. I think there actually is. If you look at Borchar's beautiful survey. And I should be giving you the notes for that. I've given you a reference to my book chapter, and that section is based on a survey with Borchar. It's made very clear over and over again in that section. So you already have that. Section 9.2. Is basically taking that survey and simplifying it to a discrete setting. He's looking at general state space Markov decision processes. This is for finite state space, finite action. Just sort of. All right. And so it might be. There might be a simpler way than computation, but I can't remember. Does Nancy this make you feel any better?
I kind of see where that would be going. I don't know.
Yeah.
I'll try to look at it.
Yeah. I wish I could. Maybe next time I'll go check myself. I can give you, maybe there's a faster answer. Okay, so I said that's it. You've got 3 algorithms now, and each of them gives you different ways of thinking about that. And now the rest of the course is all about learning in different contexts. And one is partial observations. I don't observe this state. And 2, I don't know the system. I don't know the transition matrix or something. There are examples where you don't know the cost function. In economics all the time, the cost function is preferences of individuals, and you don't know those. In economics, they love that. So there's all sorts of things you might not know, and we'll get into every one of them. Yeah.
I noticed in the formulation you have C, and then when you define half space, you get C.
Yeah. Oh no, right there. See?
So this is an arbitrary function, not necessarily the cost function you're
No, no, additional constraints.
Oh,
You know, so remember last lecture I said I might have m of these.
oh, okay.
You know, I might have different costs. You know, I want. It's hard to have to do with that politics, because I'm always thinking of a central planner who's trying to make decisions. You know, and they say, you know, I want to make sure that I don't give too many people to the people in this neighborhood. In this neighborhood, I have no lower bound. But you can imagine that's the way it comes out. You know, I have different categories of things I care about, and I'll put in constraints that I don't want the cost to be too high for the different parts. That's where it comes up. But the fact that with the randomized policy is annoying then. I mean, you know, to solve it. But that's life. That's how it is. Yeah.
So what does gamma represent physically? It's
Oh, no,
EMF?
remember what gamma is. So gamma of XU, Bayes' rule was mentioned. It's defined by, I mean, any probably mass function on pairs XU can always be factored. It's the probability of U given X times the probability of X. That's just Bayes' rule, you know. That's this is notation for probability of U given X. But so that's a randomized policy, the probability of taking action or input U when the state is X. And but this is true for this is possible for any PMF. But what's special is that pi is invariant for the resulting transition matrix, which is so that restriction is what defines this G. So it's not all probability mass functions. It's that extra linear constraint. Yeah. And and you can. I mean, it's not written this way. This looks very, very nonlinear. That's the genius, is that man found a way to make this into a linear constraint. Yeah, this looks nonlinear, it really does, if you write it out. Yeah. Yeah.
So is this all for finite state space?
No, well that's a beautiful, so the amazing thing is if you want to develop the theory of Markov decision processes, like existence of an optimal solution, it is so damned hard, except for this. This like makes it trivial. I mean, it's incredible. See, you don't define G this way. You define G as a set of all possible limits you could get of empirical distributions. I mean, it's a random set apparently at first, and then you put constraints on it, and you find out it's given as I described last time, and that holds for like anything, uncountable state spaces on manifolds or whatever, arbitrary inputs. And you're able to prove that optimal control has to be state feedback without any assumptions at all. So you can see that in Borchar's, this amazing survey he has. It's a beautiful, beautiful text. So it's useful for just, for theory, for sure. But of course you can't implement this if it's not a finite state space, an LP on an infinite. If there's an infinite number of X's and U's, this becomes an infinite dimensional LP. Good luck, Yeah.
Could you give us some intuition on what G would look like maybe for the homework column? Is there
Oh, there's no intuition.
some 2 to the third going on in there? Is it like an 8-sided?
Oh, no, I can't write it down again. Oh, no, because it involves, you've got, your variables are like cubes and things. I couldn't write down the LP very easily because gamma itself is naturally expressed as a matrix. With like row and column or column and row, and so we've got linear constraints, and you have to somehow write code which makes it into a vector, makes the constraints into matrices, So I can't give intuition. The intuition is that that one strange constraint that I wrote down is just saying that we have that, where pi is just the marginal. So pi is just, pi of x, the big thing is equal to the summation over u of gamma of xu. And that's the marginal, and that's what I meant by pi of x. Gamma is a steady state distribution on pairs x and u. So if I sum out over u, I'll get the steady state distribution on just x itself. So when I say pi, I mean I mean that. That's the definition. Yeah. So that, if you want intuition, that's it. Gamma is all PDFs for which that holds. And but then coding it is a bit awkward. You know, I've never done it. It's terrible. I've never actually coded it myself. I just feel like there's too many things to do. I was really thinking of trying to give it to you as a homework assignment, but there's so many more interesting things to do. I just don't think this is it. Yeah. No.
Okay.
Yeah, sure.
I'm just trying to understand like the how to distinguish gamma and pi. Like obviously they're related by that base rule right there. But
Yeah.
So if I was going to say, this could be naive in terms of implementation, but like just as a way to construct all gammas for a finite case.
Yeah.
Would I pick a policy, then I could, simulate the Markov chain running on that policy until like we converge to a final PDF,
Yep.
PMF, and that would kind of be like my pi. So basically, if I, how we have like P sub V, if I take some phi, then that locks P into like a
transition matrix.
Markov decision matrix. It's just
Transition matrix,
transition matrix. Then I could just multiply that, raise that to the, 100 millionth power to get the steady state version of it.
Exactly.
And then I read off a row of pi, like one of those rows is going to be pi. And then with that pi, like how do I get the policy from there? Like that.
No, you just don't. No, you start with the policy. You said you applied a policy. Yeah.
I chose the policy that resulted in that pi.
And you'll choose randomized policies.
So then I do pi times.
And then you just multiply these together, you get your gamma. Yeah.
Okay, so once I get that pi, I would do pi c to see how much, like what the expected cost was.
Well, c is a function of two variables, right? So it's gamma c you care about. Yeah. So gamma is a natural thing. That's a funny thing. I mean, if you're going to teach a course, you're going to emphasize average cost optimal control, you think the very first thing you do is it's a function of two variables, x and y. Our cost is, it was pi of c when we were in the n-controlled case. Yeah. But now I bring in a control. Naturally, I'd like to minimize the stop product over all possible gammas we get. It's so intuitively natural, it's ridiculous. Yeah.
Is gamma going to have like all three rows going to be?
No, it'll be crazy. See, well, no, in the end, the optimal gamma is going to be of this form. It's going to have a lot of zeros.
Okay.
Yeah. So, so for each x, you find the element for which this thing is non-zero, and that gives you your phi of x.
So it's basically going to be a matrix that, I said like you would take p sub v, raise it to the 100,000th power, get pi. You could construct gamma essentially by taking the elements of pi and putting them in their respective, the policy, like the indicator function that you have.
Well, if it's a deterministic policy, you get this. And if it's randomized, you'll get this.
Yes.
Yeah. Just that. Yeah. But the way, that's not the way it's done. I guess I will say this. If you look at Borkar's survey, what he does is he looks at 1 over n summation. Well, let me write it like this. You're forcing me to do this. So this is called the empirical distribution. And since we're getting to learning, and empirical distributions are like something that comes up all the time, it's not a bad idea to do this. So the tilde is just emphasizes a random probability measure. And it's a random probability. So now, in the survey, it's completely general. So we just have x and u. X could be Rn, or it could be function space. It could be any weird thing. It could be some manifold. And U could be any wild thing as well. So I wrote B there for the Borel sigma field. So sets in there. So you basically have this, and you argue that there's some sort of tightness, Or you don't, you just, but look at all possible limits. So you define G to be all possible, all subsequential limits. And I'm not going to try to make that precise, but it's the intuitive thing. I can take it, there's a subsequence that converges, I'll throw that in my stack. I'll collect them all. And that's for every policy. So not Markov, I mean not stationary,
Yeah, not deterministic.
not deterministic, but not even just randomized, but it could depend on the entire history. Because the point of this paper is to prove that the optimal policy is actually state feedback. So you start off with all possible adapted, non-anticipative, randomized inputs, and then you come up with this crazy set, but then you prove really it's not hard. It's amazingly simple to prove that this crazy set is just a simple thing I showed you last time. It's so cool. It's almost a one-liner, but you need to know the Martingale convergence theorem. You need to know about martingales. I mean, if you know a little about martingales, it's a one-liner. Yeah, but it's incredibly simple result. So I'm amending my PIA VIA notes to put in an LP section at the end that gives you a hint at why it's true. The whole proof's in my little book, I mean, it's only a few pages long. That this crazy thing has a simple characterization. Yeah.
So I think last time we said G was a set of all possible steady-state PMS.
That's how I'm trying to.
Exactly the same, or you said there was more elements?
No,
It's the same exact.
No, this looks crazy complicated because I'm looking at, well, first, we'll forget the Borel business. I mean, let's just go back to the finite state space case. I'm just emphasizing finite state case. I'm emphasizing that this survey looks at a general case. But the way, one way to look at this is to look at all possible limits of this for all possible admissible inputs, okay? And you get a whole crazy collection of probability mass functions, okay? But then you end up showing that collection is exactly what I showed you. That very simple, that the only thing that's important is that you have this invariance constraint. And again, the proof is not hard at all. It's really nothing. Yeah, it's, you wouldn't believe how simple it is, but yeah.
So all the policies in G aren't necessarily stationary.
No, back. This is a construction. So this was a mistake. Look, you come up, you first define G to be all limit points of this, okay? Where U could be any randomized policy that could depend on the entire history of the x's. So at time t, it could be some crazy randomized function of all possible xt's. Like you could pick a uniform distribution in time over the, from 0 to the current time, pick that state and make a decision on that state you picked at random. Any crazy.
So it includes all like possible policies that don't even depend on the state at all.
Exactly. I'm going to just say U equal.
So you might as well just say this
Yeah.
is like a set of PMFs resulting from all possible things you could have considered doing.
But as long as you don't predict the future, so it has to be adapted. Adapted. Otherwise, it has to be adapted. You can't. My action now can't depend on what's going to happen tomorrow. It has to be adapted.
So if we could, though, there'd probably be something more optimal.
Well,
we could proceed.
yeah, it would be more optimal. We wouldn't get this thing anymore. Yeah. I mean, G would get much bigger. It might become everything. I don't know. Yeah, but the thing is that this thing that looks so big turns out to not be big. You end up showing that this set of all possible limits is just what I described. It's all PMF satisfying this invariance constraint. That's it. That's it. So you start up something huge, and then you show it's not big at all. Yeah.
I think I'm still stuck on the notation of phi of u given x.
Yeah, come on. No, come on. On the top of the hill, I drive with probably half, or I don't drive with probably half. That's an example of a randomized policy.
So is that just like a linear interpolation on, so in that figure with the corners?
Yeah.
Is it just if you're
Yeah.
3/4 of the way from between driving and not driving, then you'll have probably 3/4 of.
Now you're trying to average the actions instead of averaging the probability of the actions. I mean, U only takes on two values again. It's driving or not driving, right? And so phi of U is a probability.
Right.
Yeah. I'm not taking an average of actions.
No, but is the probability that average?
Yes, it is.
So it's just like a
When you go along between those corners, yeah, if you're halfway through, probably a half.
That's the probability.
Yeah, exactly, yeah. Yeah, you got it.
Well, like, we should be clear that that diagram you were drawing was not drawn in the state space, it was in the set of all.
Yeah, I mean, yeah, absolutely. Yeah, you're right. I mean, absolutely. Caveat, it can be, but not necessarily, because that diagram was in the whole X use.
I can imagine, since the corners were those deterministic policies, as you move away along one of those edges, it's a policy that's like, more percent of the time, the point that it's closest to, less percent of the time,
Well, no, but you can make it precise. I mean, I don't want to go. We shouldn't spend too much more time on this. But but it's good. If this was like gamma 3, and that was gamma 28, where these indices go to. Remember, we've got u to the x, right? So that's not very big for the Sybil Homer problem. But suppose I take that point there, gamma is equal to 1/4 gamma 3 plus 3/4 gamma 28. I'll let you work it out. It's really simple. I'm not going to do it. I'll let you work it out. But you can think there's a quarter there and a 3/4 there, right? So this thing here is only going to take two values: a quarter, three values. A quarter, 3/4, or 0.
And you'll never be like in the middle of some face. You'll always be on an edge.
No. I'll give you an example. If I'm on this one-dimensional line, it'll be two guys. Here, exactly. If it was on a face, it's different. I mean, yeah. I'm just looking at this line. Absolutely. Yeah. So it is. I mean, so it's. Yeah. I don't. Yeah. Wait a second. Wait a minute. I'm sorry. The randomization is only over two states. I might have got my numbers wrong. I think I just made a mistake. So let's all go revisit that. In fact, now I'm going to make it. You force the homework problem on you all.
Okay.
I think what I just said is false. The numbers are not a quarter, 3/4 for the policy.
I agree.
But there's only two randomization over two states. I mean, two actions for each state. That's what. Yeah, that's the truth. The numbers you'll find are exotic. Yeah, because there's a division that goes on. I mean, in order to define this guy, you've got to divide, and so yeah. So the probabilities, for every state there'll only be two actions that you'll randomize over, and the probabilities won't be there. Okay. Be prepared. That'll be a homework problem next summer.
So where is pi in that, or pi's not there?
No, pi. There's pi.
But no,
You have to work it out. That's why the homework problem is going to take you a few minutes to do.
So to be clear, if we imagine that gamma 3 was associated with the policy of, say, always driving.
Yeah.
And gamma 28 is the policy of always not driving.
Yeah.
This is just as examples.
Yeah.
Then, like, this gamma that you're saying that's 1/4 one way and 3/4 the other one is not going to be, like, 1/4 the time driving.
No, yeah, I screwed up there. Yeah.
Because I wanted to I don't think it's that
No, it's not. No, it's not. It's yeah, exactly.
Distances in the gamma space are not going to be.
Exactly. There's a division that goes on in getting the policy.
Yeah.
See, given gamma, you can get the policy, but it's through a division. That's why. Yeah.
Another question. The speed of u next is conditional probability. So as we're minimizing gamma and g, are we cycling through these fees as part of the...
No, you type LP solve in MATLAB.
Okay. So those aren't determined by your system, or is it...
No,
Where those come from?
you know what the dot product is, you know what the objective function is, so the matrix that you have in the current homework problem, you have to interpret that as a big row vector in MATLAB. And those linear constraints I showed you last time that could be represented as a linear constraint. And you've got to somehow represent that as a bunch of linear equations in MATLAB, and you can. You know.
Where does phi pop up?
So we're taking
No,
the phi.
no. You don't write it this way. Look, I don't want to have to write down again. If you look at your notes, it's embedded here without. I didn't write it this way. I wrote it in a very, very special way, so phi didn't have to appear.
Okay.
Yeah. No. There's a really cool. That was the genius of man, that he was able to write in a way where you didn't have to. You have linear. You get an LP with the variables gamma. If you try to make the LP and phi and pi separately, it would not be convex. It wouldn't be anything. It's very, very special. So this can be represented in gamma as a linear constraint, as I showed you.
But in any
Yeah.
implementation, you have to basically you're picking a phi, and then
No.
you have to iterate over
No. Well, the simplex method will do that. Whatever the computer implements. I mean, not that you're going to code an LP solver. So if you use simplex method, it will bounce around the corners. The simplex method hops around extreme point to extreme point, and that's why it's often not liked. And there's interior point methods that would always would go along and cycle around, in the interior. And
How do I say subject to gamma in G to a computer?
all right.
That's how you do it.
I think is it LP solve? I don't remember. Oh, it's something like that. It's something like that. There it is. So, taking what I showed you before and making it into that takes some work, because your z variable, which is gamma is shaped like a matrix. You got to stretch it out and make it into a vector. And A up here was like a cube. There's some really weird things going on. You got to convert that into a matrix. So there's a bunch of coding work to make it into that. But then it's wham, and there's two approaches to LP solving. The most common, again, simplex method. You go wham, 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 gamma star. I know that's gamma star because that is a subspace where gamma c is less than or equal to gamma star. Take that half space, that corner, that's the optimal policy. And so simplex method would go wham, 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 and get it. And interior point methods would go shoo, and you get some beautiful trajectory that would go towards it. And so interior point methods, you'd always have a randomized policy to stepping out of it. Yeah.
I need elaboration on A.
Yeah, no. Well, I mean, I had equality constraints, but equality constraints can always be converted inequality by.
Okay, so the equality constraint that we would be considering is somehow pi piece of.
Well, go back and look at your notes. I won't write it down again. What time is it? But if you go back and look at the strange equality constraint I had on gamma, it was exactly this. It was just a weird way of writing it. Yeah. I had, I used the fact that this was this. So instead of writing pi here, I wrote the summation of a u of gamma xu on the right. And this I wrote in some very strange way. You'll have to look at your notes. Yeah. So it's, I mean, maybe it is worth it. I don't know, for you guys to try it out on that guy. Yeah. It wouldn't be that hard. With that simple example, that matrix A is, I don't know, be 12 by 3 or something. I mean, it won't be that bad. I guess you're forcing me to torture you. All right. It's your fault. It's too bad there isn't a problem you can actually see things. I mean, it's like the simplest problem would be polyhedral in 10-dimensional space or something like this. So, let's do it. You know, here's where we are, and well, forget that. So I told you about this awful term from operations research, a Markov decision process. So it's, you know, controlled Markov chain. I wish we could say that, but we can't. But PO at least is reasonable, partially observed. And, you know, I'm going to just put this in a form that's more concrete. So these controlled Markov chains really are always of this form, okay? I know it might not seem obvious for that homework problem, for example, but you could do it. It would be very artificial looking, but even for that, you know, that thing on Pluto that's looking for energy, you could write the new state as a function of the old state, the input, drive or not drive, and some IID noise. You could do it. I'm not going to ask you to. So anyway, that's a controlled Markov chain, and here's our observations. And the big assumption is that the W and N are IID and also mutually independent. Yeah, and that's all crucial. You know, this is all fragile. If you perturb those assumptions, you're in trouble. Yeah, if there was dependency in these guys, you'd have to change the state. You'd have to start, you know, I don't know. You'd have to call that a state, you know, and then you may be able to handle it. So yeah, so it's not that bad. Yeah. Well, even that wouldn't work. Like, it's not that easy. No. There are tricks, but it's not that easy. So anyway, so we're going to just stick to that. So these guys are, the pair process IID, the observation noise, and the disturbance are independent. When you say it like that, it doesn't sound too bad. That's a disturbance to a physical system. It's the wind hitting the airplane. That's the sensor noise, you know. Yeah. Well, shush. Exactly. You definitely got me. Yeah. And so now the problem is we want to choose our controls not as a function of x, but as a function of y. Unfortunately, like, this is the situation in almost all real applications. You know, we don't observe the entire universe. X is some massive thing. And as soon as you go through and you make this into a partially observed problem, so your input's a function, maybe a randomized function, let's forget that, but a function of the measurements, things get so much harder. So conceptually, things don't change at all, it turns out. You'll see. You still get state feedback, but it's a different state. And so, how many of you, so you were supposed to have taken stochastic methods, but I guess a lot of you didn't. You did, yeah.
I did not.
Oh, you did not, yeah.
It's been
Well, the thing is, I mean, the thing is that you need, in order to make this work, you need to know how to generate the conditional distribution of x given the y's, you know? And what I'm going to say to you all is, go to Wikipedia, or I've got links for you to look at the algorithms. There's an algorithm, and I'm not going to put it on the blackboard. It's just tedious. It doesn't have many concepts, and you can get just like the LP. I mean, well, I did give you that, but I mean, I gave you mainly what emphasizes the concepts. I'm not going to tell you what the initial distribution of that given that is. I'm just going to tell you it exists and give you some structure. And what we're going to find is that we can convert this into an MDP. So we can make a completely partially observed MDP into a full regular MDP like we've been talking about all along.
You
So-
have no assumptions of like linearity.
No, nothing. It's a magic. And it all goes back to this thing about well, we'll get back to this. Why you can get away with murder, I'll explain now. But yeah, so.
I'm sorry, I sort of lost, what is partial?
Right, no, that's what's right there. That's the definition.
Okay.
The definition is I'm observing this, but not that directly.
Okay.
Yeah.
Not to be the
Oh,
same
that's
as
why the
control
flow is
variables.
partial.
Yeah. And so, so we still have our controlled transition matrix. Yeah. And by the way, that's notation you'll also often see as well, by the way. I mean, yeah, I said you had some, what?
Yeah, so does that, where's the unobservability come into play here? 'Cause I'm-
No, it's
you wrote
observable. It might be perfectly observable. No, I'm not talking about, observability is not an issue I'm talking about yet. All I'm just saying is that I am restricting my inputs to be functions of y.
Which
Yeah, so, well, it might be, G could be 0.
equals
G-
some function of x with extra noise in it, which is independent of whatever noise x sustains.
Yeah, that's right. So there's less information. It might not be. I mean, it might not be. I mean, G could be the identity function, and W could be 0, in which case it's full observations.
Well, I
But
guess what I'm asking
yeah.
is this partially observed is because of the noise, not because some states are not observable?
no, it also could not be observable. I mean, G could be, G could be an RD, and Y could be a scalar.
Okay.
You know, there's all.
Because
Yeah.
making decisions based on a function of the states rather than the states.
Yeah, yeah. G might not be invertible. You know.
Usually coming from the terminology like
Yeah.
observable, and when we're like,
Yeah.
I would rather this say indirectly observed.
Yeah, that's just the language, but that's the standard control language. That actually is mainstream. Yeah, and yeah, I can see how that might confuse things, but yeah, so there's some notation there.
So, just
Yeah.
to be clear, like, so if G is invertible, it's fully observed, is it, or like will it be?
What? No, if there's no noise and G is invertible, then sure, I can just, then Y and X have the same information, yeah. Yeah, of course, yeah. Yeah, but yeah, that's not going to happen. So, so we know what that means, and it's often written this way as well. And this is going to give this full map. I'm just going to use notation like this. You know, there's a little p here, which is, this is nice because it emphasizes I've got a probability mass function, but the probability of x prime given x and u, just like this. Okay. And this is a probably observing y1 given the state is x1. And I'm sorry, primes. I didn't mean 1. Sorry about that. Okay, so we had this thing already, and then we've got this thing here. So those will really be our primitives, okay? It's just, I think this is more concrete, you know, that I've got this recursion for x, and I've got a noisy function of the observation, of the state. The observations are a noisy function of the state. And the goal is the same, okay? We basically would like to choose phi so that the average cost is minimal. How the hell are we going to do that? All right. And by the way, these notes that I'm looking at right now, they'll be yours once I clean them up a bit. They're a little bit messy. So I'll give you some references as well. But what I'm saying right now is all written down, so you don't even have to take notes. All right, so what do we have to do? So first of all, what do you think that this is going to look like? I mean, what is an optimal, you know, what is phi star going to look like? I mean, what the hell, you know? Well, we're going to need to estimate the state. And for this, I need that mathematical notation about sigma algebras and all that. So if I write, if we've seen this before, if I write H is in, wait, actually, I'm going to keep the same notation. Yeah, good. If so I know that FT, so FT is a sigma algebra, and usually define it, a set is in that sigma algebra. Can you let me use notation and say a function is in the sigma algebra as well? Okay, just bear with me. But so, saying this means that H is in function of the observations. So just like YT is in, UT is in this script YT. Okay, so if we had really good estimates of x, then we could just do what we've already done. If we had really reliable estimates of x, we could just say, well, to hell with it, I'll just stick in my estimates. And maybe you can. So there's two approaches to estimate x. And let me explain it. I don't need any of this. I will, yeah. Yep. Because these will be our primitives. I mean, I'm not going to have to write down f and g. Again, I'm chalk conscious. I'm going to have, what you're going to give me if I want to solve a partial observed MDP is my state transition matrix and my output readout map or something, my statistics of my measurements.
That's notation.
Yeah, that's his notation. Yeah, I can imagine it'd be so hideous to try to use this. This is just conceptual, it's not useful. Yeah, just that my output is a noisy function of my state. My measurement is a noisy function of my state. Right. And we'll come back to that. Now, there are too many t's around, so forget all this for a second. Suppose, let's look at generalities. Okay. Let's say z and y random vectors, y is a string here, and z some other vector. And do you all know how to think about estimation? I'll remind you. One is the so maximum a posteriori probability. All right. I'm sorry. All right, so this is just to get us in the mood. So I might try to come up with an estimate. So I want a function of the observations that is close to z. Well, I think the most natural way to do that is to say, I want an estimate for which the probability of a dead-on hit is the highest, right? Well, first of all, you can't compute this, and secondly, why would you do it? because probably this maximum is probably 0.004. It's, you know, getting it dead on hit in a large state space. You know, Z is in a big space. The probability of getting it dead on hit is probably really low. So you might do this, you know, if you've got a system with not a lot of noise, and you might be able to come up with some approximation for that. But unlikely that's going to be what you do. All right, so nah, nope. We're not going to do that. The other problem is that we've got so many things we have to estimate. It turns out we're not just trying to estimate the state. There's also, you'll see, we have to estimate, in order to make this thing work, you have to estimate a lot of functions of the state, not just the state. So we would have to be doing this for all sorts of things. It wouldn't be sustainable. So the other thing is a conditional mean. Well, forget that. No, the minimum mean square error estimate. I said nope now. All right, so I take Z and I look at the error. It's say the vectors, I take the norm and square it. And I take the minimum overall size. And what do you get? You should all know. So not the average.
Something like covariance inverse something.
Oh, well, no,
DV5.
this is over all nonlinear functions of the data. So there's no, yeah, so there's no, well, there is a least squares problem here, but it's infinite dimensional. Yeah.
You need to be saying by C.
Yeah. So again, in both cases I have this. And if I minimize over all, oh yeah, sorry, Y. Yeah. 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 And so what's the answer? Oh, I don't
I know
know.
what it is if you assume that phi is of the form, you know, like
Yeah.
ax plus b, or ay plus b.
Okay, wait. In stochastic methods, were you about to say it? It's
I was saying it's like covariance.
no. It is in some way. I mean, you can make that precise, but you got to go to some abstract setting. But because it doesn't give. I mean, it doesn't know what psi is.
It's the expected value of z with respect to the probability density, probability function, you know, p of y,
Z given
y.
Yes.
Yes.
What's the conditional mean of that? Yes, absolutely.
That's the shortest
So
way of saying
exactly.
that.
So Z hat in this case equals psi star of y in this case is exactly what you said. It's the conditional expectation of Z given y. And if we did have a density, but we don't. I mean, y is going to be a probability mass function. You know, well, anyway, I'll write it like this. It would be, I want to forget it. I'm not going to write it out because it depends on whether these guys are discrete or continuous, so you have to get that. I mean, anyway, you know, go and review what that means. Okay, so the conditional expectation, one definition is a solution to the mean square, the minimum mean square estimation problem. That's a definition.
In your previous problem statement, you kind of made it sound like we were given the transition matrix and we were also given this like observation probability p of we were using x and y before, but you gave us the probability of y given x. You said that that's kind of just something that's handed to us.
That's the model.
Yes, that's
We've got a dynamical model. So we know the probability of y given x.
So we like Bayes' rule to get.
Yeah, that's right. No, that's a trivial thing. This we can get using. So when we apply this, so this is what we'll use. And we're interested in things like, for example, z equals xt, and y equals y0 up to yt. Right? And then we're talking about, you know, z hat is x hat t given t, you know, so it's the conditional mean of x for states up to time t. So this notation, Oh, I got F here. God, I'm getting sloppy. I wanted to make a fancy Y. So I changed that F to a Y. You know, I need a YT. FT was used for something else. And so,
So does that mean UT also belongs to YT?
yeah, well, absolutely, because UT is a function of stuff up to YT. Yeah, absolutely. So if you were really naive, you'd say problem solved, I can compute this, and you could try UT is equal to phi star of x hat t given t. It's not optimal except, but it is in certain cases it works. It's called certainty equivalence. It's horrible language, I'm sorry. I didn't make it up. Okay, and again, it usually fails, but it's worth trying out. You know, if somebody gives you a problem, you find the optimal solution, you know, assuming you have full state information, you compute the conditional mean and plug it in.
This is like separation principle.
Yeah, and that's right. In the linear case, it works. In the linear case, there is a separation principle, and Anand will give a lecture on that probably. I don't know. We'll see. But how could this fail incredibly? Example of the homework. So the state takes on 3 values. Well, let's give them numbers. You know, 1, 0, and minus 1. You know, 1's the top of the hill, 0 is the middle, minus 1 is the bottom. What's that going to be? It's going to be in between. So phi star is only defined on 3 points. Well, this takes on real values between minus 1 and 1.
Oh. Okay, a simple example.
So maybe in that case, if you're going to use certainty equivalence, maybe you should try to use that instead or something, or you know, you have to quantize somehow. You'd have to somehow project this or use this. Or,
This is kind of like
you know.
applying the framework of estimation can't be used on discrete state spaces.
No, it can. It's just that that's not the right way to do it. This is just one dumb thing you might try, and it's just worth mentioning. And it often fails. I mean, it fails because it's not feasible. It fails because it's not enough information. The conditional mean is not enough information. You need, what about the conditional variance? I mean, conditional mean is just not enough information to make a decision. So that's not going. That will not be it. That will not be that easy, unfortunately.
What is the notation t given to?
Oh yeah, I'm right there. So it's a common notation for estimation that I'm on my estimation at time t given observations up to time t. There's a common shorthand for that. Yeah. But it's 3 o'clock, so we have to take a break, I think. Otherwise, we're nuts. So, yeah. So anyway, the reason we do this is because we sure as hell aren't doing that. There are so many things we need to get conditional expectations of. And x is the least important. There'll be all sorts of functions. And in the rest of the lecture, we'll tell you what all of them are. We'll list them, like the corners of G. Okay. All right. All right, so take a jog around the building and